Now we will learn how to download and use GMFlow model. Firstly, we should download GMFlow repository in our notebook. To do that, we just need to type get a clone, and here we should put the link of the repository. Now we will run this cell, and that's it. Now we downloaded this repository. Now we will import GMFlow from GMFlow.GMFlow.GMFlow. Okay, let's run this cell. Now let's create our GMFlow model. So we will type GMFlow model equal to, and here we will use this GMFlow class to create our model. We will make feature channels argument equal to 128, num scales equal to 1, upscale factor equal to 8, num head equal to 1, attention type swing, ffn dim expansion equal to 4, number of transformer layers equal to 6, and we will send this model to our GPU. Now we created our GMFlow model, but the weights inside this model, they are random. So we will replace them with the pre-trained weights. Actually, they trained a model with the same structure previously. We will take the weights of that model and put them in our model. You can download these weights from GMFlow repository. We just need to go to this place here, to click on Google Drive here to download it, and you will get many different pre-trained weights files. As you can see here, we will just select one of them. We will use this one, GMFlow Centel, to find optical flow. We will put it in our Google Drive. Now we have this GMFlow Centel in our Google Drive. We will copy the path of this file and we will put it here. So what we will do here, actually, we will import torch library, and we will use torch.load, and we will put the path of this file, and we will get this checkpoint. You will see many different things inside this dictionary. We will take just the weights from it. How can we take the weights from this dictionary? We just need to type checkpoint, and we should open these square brackets, and we should type model, and that's it. These are the weights that we will put in our GMFlow model. Now let's put them in our GMFlow model. To do that, we just need to type the name of the model, GMFlow model dot load state dict, and here you should pass the weights, and that's it. Now we can use this GMFlow model to find the optical flow. And because that we don't need to train this model, we just need to use it. So we will type GMFlow underscore model dot evaluation like this. In my Google Drive, I have many images. I will take two of them. Okay, the first image, which is this one, and another image, for example, this image. Okay, let's take them. We will import CV2 package. We will type import CV2, and here cv2.image read, and we will put the path of the first image like this, and let's call it image 1, and we will take the second image or image 2. Let's take the path of this image, for example this one here. So now we have the first image and the second image. Now we will change the order of the color channels from BGR to RGB, which is something important actually, because they trained our GMFlow model previously on RGB images, not BGR images. We will do this for the first image and for the second image. And as you can see here, here is our image, our first image, and our second image, this one. That's good. Now these two images, they are NumPy arrays, and we want to pass them through our model, PyTorch model, so we should convert them into tensors. So let's convert the first one, image 1 equal to torch dot from NumPy, and we should open these parentheses, and we should pass our image 1 here, and we should change the order of the dimensions. Let's see the original dimensions in our image 1. So we will type image1.shape. Here is the first dimension, the second dimension, and the third dimension. The first dimension, it is the height dimension. The second dimension, it is the width dimension, and the last dimension, it is the color dimension. What we will do here, we will take this dimension and put it in the first. So we will make this dimension the first dimension, and this one the second dimension, and this one the last dimension. Let's do it. We will use permute method, and we should open these parentheses, and here we should put the index of this dimension, which is 2. The index of this one is 0, the index of this one is 1, and the index of this one is 2. So we should put 2 firstly, and we should put 0, and we should put 1 here. And we should convert the type of this tensor to float, and we will send it to our GPU. Okay, we will do the same thing for the second image. Now we prepared the input to our GMFlow model. Now what we will do, we will import input pattern class from GMFlow folder, and we will use it to pad these two frames so that the dimensions of each one of these frames are divisible by 8, which is something required by our GMFlow model. So let's import this input pattern. We will type from GMFlow folder dot utils folder import everything. Okay, let's run this cell. Actually, this input pattern is available in utils script inside utils folder, which is inside GMFlow folder. So we will type from GMFlow folder dot utils folder dot utils file import everything, and now we can use this class. Let's create an object for this class. We will call it pattern object, which is equal to input pattern class. And here we should pass the shape of any one of these images. Let's take, for example, the first image. So we will type image1 dot shape, and here we will make padding factor equal to 8. Now we can use this pattern object. Now what we will do, we will use this pattern object dot pad method, and here we will pass the first frame, and we will pass firstly the first frame, and we will add another dimension to this frame, which is the batch dimension. We just need to open these two square brackets, and we should put none between them like this. By doing this, you will add new dimension at the first, and the length of this new dimension equal to 1. It means a batch with one sample. And the same thing with image 2. And this function will return image 1 and image 2 after padding. And now we will use our GMFlow model to extract the optical flow. Firstly, we will type with torch.noGradient to avoid computing gradients during doing inference or during using our GMFlow, because as you know, we don't need to train our GMFlow model. They trained it previously. And here we will type optical flow dictionary equal to GMFlow model. And here, firstly, we should pass the next frame, and after that we should pass the first frame or the current frame, image 1. And here we will make a tension splits list equal to this list here with just one element, which is equal to 2. And we will make correction radius list equal to this list here with just one element, which is equal to -1. And we will make this parameter probe radius list parameter equal to this list here, which has just one element, which is equal to -1. And we will make prediction by direction flow equal to true, which means that we will use our GMFlow to extract forward optical flow and backward optical flow. Now let's see what is inside this optical flow dictionary. Let's put it here and let's run this cell. And as you can see here, here's our optical flow dictionary. Inside this dictionary, we have our optical flow. Let's extract it from this dictionary. Let's open these two square brackets and type flow predictions, and we will get this list. Okay. And now we will extract our optical flow from this list. We will just need to open these square brackets and put 0 here. And that's it. Now we have our optical flow. Actually, our forward optical flow and backward optical flow. We will learn how to extract each one of them from this tensor. Firstly, let's extract forward optical flow. To do that, we just need to type optical flow prediction, and here we will open these square brackets and put 0 between them, which means the first element in this optical flow prediction tensor, which represents our forward optical flow. And as you remember, we added paddings to our images before passing them through our GMFlow model. So these paddings will also appear in our forward optical flow and backward optical flow. So what we will do, actually, we will remove them. We will use our padder to do that. So we will type padder.mpad, and here we will pass our forward optical flow. And here we will also again add the batch dimension to this forward optical flow by opening these square brackets and putting none between them. And here is the new dimension: 1 times 2 times h times w. This optical flow represents the movement from the current frame or the first frame to the next frame. And as you can see here, the width and height of this optical flow, it is equal to the width and height of our original images, which means that we have a vector with two things, x and y, for each pixel. This vector will represent the amount of movement of that pixel and the direction of movement when we moved from the previous frame to the next frame. In other words, when we add this vector, this x and y, to our original location of that pixel in our previous image, in our previous frame, we will move this pixel to its new location in the next frame. And now we will extract backward optical flow. This optical flow will represent the movement from the next frame to the current frame or the previous frame. So backward flow equal to padder.npad, and here we will type optical flow prediction, and here we will pass the index of this flow, this backward flow, which is the second element in our optical flow prediction tensor. And here we will add batch dimension to this backward flow. And here is the shape of this backward flow. The first dimension, it is the batch dimension. The second dimension represents xy dimension. And here we have the height and the width. And now we will take the shape of this forward optical flow, and we will get the batch size, the number of channels, the height and the width of this optical flow. Let's run this. And as you know, the size of this optical flow, it is similar to the size of this optical flow. And now we will create a grid of locations. We will use torch.meshGrid, and we will pass torch.arrange edge to it, which represents all y locations of our pixels from 0 to 463, and the same thing here, torch.arrange w, and this one will represent all x location in our image from 0 to 811, and we will get two things, y and x. Let's display this one. Here, this y tensor will have a y value for each pixel in our image. For example, here, y equal to 0 for this pixel, this pixel, this pixel to this pixel. And the same thing here, y equal to 1 for this pixel, and this pixel to this. So this tensor will have a y value for each location in our image. Now let's display x tensor. X location for this pixel equal to 0, x location for this 1 equal to 1, x location to this pixel equal to 2, etc. So now we have y location and x location for each pixel in our original image. And these locations, actually, they are the original locations of our pixels. Or in other words, the locations of our previous frame. So now what we will do, we will change these locations based on our forward optical flow to get the new locations of our pixels after moving from the previous frame to the next frame. Now what we'll do, we will stack this tensor, x tensor, which represents x location for each pixel, with this tensor, y tensor, which represents y location for each pixel, the original y location for each pixel, or the y location for each pixel for the previous frame. Here we will create a new dimension and we will stack them along that dimension. Let's firstly see what is the shape of X tensor. And here's the shape of this tensor. It is similar to the width and height of our original image, and the same thing for this Y tensor, as you can see here. So now what we will do when we use this torch.stack method, we will create a new dimension. We will put it in the first, okay, and stack these two tensors on that dimension. Let's see the results. And here's the result. We created a new dimension and we put it X and Y tensors along that dimension. And now what we'll do, we will add another dimension with length 1 by opening these two square brackets and putting none between them. And here's the result. This dimension will represent the X dimension. We will convert the type of this tensor to floats rather than integer and send it to our GPU. And we will add our forward optical flow, or in other words, the amount of movement and the direction of movement that each pixel in our previous frame need to move to the next frame. And we will add all these vectors to our original locations to get the new locations of our pixels. And here is the result. As you can see, we will put the result in this variable wrapped grid using forward optical flow. Now we will do normalization for these new locations in our wrapped grid using FWD. Firstly, we will take the new X locations from our wrapped grid using FWD, and we will divide these locations, X locations. We will divide each one of these X locations by the width of this wrapped grid using FWD tensor minus 1. This thing will make the highest value in this X new tensor equal to 1 and the lowest value equal to 0. And we will multiply the resulted tensor with 2, which means that we will make the highest value in the new tensor equal to 2. And we will subtract 1 from the final tensor, which means that we will make the range of values of the resulted tensor between 1 and minus 1. So now we have this normalized wrapped X grid FWD and normalized Y grid FWD. We did this normalization process because it is important to use these locations to change the locations of the values of our pixels based on these new locations. Now what we will do, we will stack these two tensors, normalized wrapped X grid FWD and normalized wrapped Y grid FWD, and we will put this new dimension in the last. Here you should know that the size of this normalized wrapped X grid FWD equal to the batch size times the height times the width. Okay, now what we will do, we will add a new dimension at the last, and we will stack these two tensors along that dimension. And here is the final shape: batch size times height times width times 2, which will contain the first and the second tensors. Now we have normalized wrapped grid FWD. Now we will do something called forward-backward consistency check. We will do this process to find the occluded pixels, the pixels that were hidden in the previous frame and they showed up in the next frame. These pixels will have inconsistent optical flow. So we will do forward-backward consistency check to find these pixels. Actually, here we will use the forward optical flow and the backward optical flow to find these inconsistent regions, the occluded pixels. Let's learn how to do that. Firstly, we will import torch.nn.functional as fcapital. And here we will wrap our BWD flow based on our normalized wrapped grid FWD. Think about it like this. Let's say that we have two frames. Here is our previous frame and our next frame. Okay? And here we just rotated our head like this in the next frame. Now let's draw our backward optical flow. Okay? It will be in this direction. Or something like that. Okay? Each pixel inside this head will have its own vector. Okay? When we add these vectors to this grid of the original locations, we will get a new grid of locations for the head. Let's say that this is our new grid of locations. Now what we will do, we will wrap our image, especially this region here, based on these new locations to move all this information inside these locations, all these pixels, to this region. Okay? That's what we mean by wrapping. What we are trying to do in this consistency check, we are trying to use forward optical flow tensor. This tensor will have many vectors, one vector for each pixel, okay, in our image. But here we are trying to focus on the movement parts in our image, so we will draw just these few vectors. Each one of these vectors represents how much this pixel needs to move and in which direction to reach to its new location in our next frame. Now what we will do, we will add these vectors to our original grid of coordinates, XY grid. Here let's take just these vectors, we will add them to our original locations to get new locations. Okay? And what we will do actually, we will use these new locations and we will move these vectors of our backward optical flow tensor based on these locations. We will change the locations of these vectors based on these locations here. So we will get something like this. As you can see here, we will get something like this. Okay? These vectors now, they are here. We wrapped these vectors based on these new locations that we got from our forward optical flow. And finally, our vectors from our backward optical flow, they are available in the same region of our of the vectors of our forward optical flow, so we can add them together. Okay, and because the direction of these vectors of forward optical flow and backward optical flow, they are in opposite directions, so in other words, we are trying to subtract them to find the difference between backward optical flow and forward optical flow. And now what we'll do here, we will also again stack x and y along this new dimension 0, and we will add another dimension which is the batch dimension, and we'll convert this tensor into float and we will send it to our coda. It is something similar to what we did previously actually. And this tensor will represent the locations of our next frame. We will add to it BWD flow, our backward optical flow tensor, to change these locations to the locations of our previous frame. And we will get wrapped grid using BWD. And we will do also normalization to get normalized wrapped X grid BWD and normalized wrapped Y grid BWD. And we will stack these two tensors along this new dimension, and here is the final shape, the batch size times the height times the width times 2. And here what we will do actually, we will wrap this FWD flow, or in other words, change the location of the vectors inside this FWD flow and move them to these locations inside our normalized wrapped grid BWD. By doing this, we will change the locations of the vectors inside FWD flow and move them to the previous frame. And by doing this, we will be able to find the difference between the wrapped FWD and BWD. In ideal case, the difference should be 0, but as you know, we have occluded pixels. These occluded pixels will create differences, and we will use these differences to create a mask. Now we will get wrapped FWD flow with BWD by passing our FWD flow and normalized wrapped grid BWD. And now we have two things: wrapped BWD flow with FWD and wrapped FWD flow with BWD. Now let's find the difference between them. We just need to add our wrapped BWD flow with FWD. By doing this, you will see the difference. And the same thing with difference BWD tensor. We will add wrapped FWD flow with BWD to our BWD flow to find the difference, to find the occluded regions, and we will find the magnitude of these differences. We don't need direction here, we just need magnitude. Each occluded region will have larger magnitude. To find these magnitudes, we just need to use torch.norm function. And now what we'll do actually, we will compute the length of each vector in our FWD flow, okay, using torch.norm. and we will add these lengths to the length of each vector, and we will get flow image, and we will multiply this flow image with 0.01 plus 0.5. Here we created this threshold that we will use to create the mask, and now we will create the mask. Let's call it FWD occlusion, which is equal to, we will take difference FWD if the length of any difference vector inside this difference FWD it is greater than threshold, our threshold. In this case we will make it equal to 1 or true, otherwise we will make it equal to 0. We can also call it mask tensor, and here what we will do, we will send this tensor to our CPU and change the place of our dimensions, and we will make the type of this tensor equal to long. Okay, and we will convert it into numpy, and we will multiply each element inside this tensor by 255. Okay, and here's the final result. Here is the mask. Okay, we will use this mask a lot when we are trying to do video to video animation with a stable diffusion model. We will use it to fix the background and to keep the same face during the animation. We will learn how to do that later. Now let's say that we want to wrap our image 1 to image 2 using our FWD flow, forward flow. How can we do that? To do that, we just need to find the shape of our image 1, and we will get the batch size, the number of channels, the height and the width of our first image. And what we will do here, we will create our grid. Okay, and we will do same as what we did previously. We will get this wrapped grid using FWD, and here we will find our normalized wrapped grid FWD. And to wrap our image 1 to image 2, it's easy. We just need to type wrapped image 1 with FWD, and here we will use a grid sample, and we will pass our image 1, our previous image, our previous frame, and we should pass our normalized wrapped grid FWD to get the result. Now what we will do, we will display our wrapped image 1 with FWD. Okay, here we have the batch dimension. We will take the first sample in this batch. As you know, we have just one sample, which is our image, our wrapped image, and we will change the location of our dimensions to be able to display them, and we will send our image to CPU, and we will convert it into numpy array, and that's it. And here is the result. It is not perfect actually, and this region here, it is the occluded region. Let's mask this region with our mask that we created previously. Okay, firstly let's divide this mask by 255 to make the highest possible value here, the result equal to 1, and the lowest possible value in our mask equal to 0, and we will convert the type of this tensor to unsigned integer 8, and now we will subtract the resulted tensor from 1, and let's display our final image, and that's our final image. That's great, and we masked the occluded area. Okay, that's great. These things: forward optical flow, backward optical flow, and occlusion mask to build shape aware system in our video to video machine. Thanks for watching.